Hello everyone and welcome to this new video. In this third video that will be part of a series about abstract algebra, we will talk about the dihedral groups and we will explain a little bit the intuition behind them and prove some results about them and in general just introduce them. So let's start by explaining what the dihedral group is. So we all know, we're all familiar with the idea of a regular n-gon. For example, we can take an equilateral triangle as an example, or a square, or a pentagon, for example, so like this, and so on. So yes, hexagons and heptagons and so on. So we now pose ourselves the following question. So let's label the vertices of these polygons. I'll do it just for the first one, which is this triangle. So now the question is the following. We want to find all transformations of this polygon, all mappings that map this polygon here into the same shape. So that map this polygon, in this case this equilateral triangle, into the same place, we could say. More technically, we should call them isometries. But so, for example, one such example of a transformation is if we take this triangle and we imagine, let's imagine that we rotate it clockwise, so we get B, A, C, like so. So this, we can imagine that we have this triangle somewhere on a plane, so on the table maybe, and here. Imagine we have this triangle here on the table, and we take it, we rotate it, and then we put it back in place. In particular, this is a 120-degree rotation. So, so imagine we have this triangle here on the plane. We take it, so we have it on the plane. We lift it up. Oops. Okay. And then we rotate it 120 degrees clockwise. So the result will be this. And then we put it back in place. The result, we could say, occupies the same space as before. So this is one such transformations of that we would want. So this is an example. So another thing that we want to keep in mind is that our goal is to get all such displacements of this polygon, in this case of this triangle, but we do not care how we achieve it. So for example, we could achieve this displacement here that I showed you, and now but with a 120-degree rotation, but we could achieve it as well with a 480-degree rotation, and well, we could achieve it also by rotating it counterclockwise, but this time 240 degree. And so there's really an infinite way to achieve this, we could say, this configuration here, starting from this one. So our interest is not about how we get to it, but rather just the end results. So now that we have in mind, that we clearly understand what we want, let's go there and actually find all the ways we can displace this triangle with the rules we stated. So we will start this discussion with the triangle because maybe it's the most intuitive and easiest examples. Later we will generalize this discussion to general regular n-gons. So first of all, let's think about how many possible reorderings of the vertices we can have with such a translation. So in this case, the number of vertices is 3, and well, you can convince yourself that all the possible reorderings of the vertices such that the end result is still a equilateral triangle that occupies the same point in space is 6, which basically agrees with the number of permutations of this set, which is 3 factorial, which is 6. However, in general, this would not be true because we will have to be careful about preserving adjacency in the polygon, of course, because otherwise we would basically get a shape that is not what we want. So, but in this case, since we have a triangle, in this special case of the triangle, it works that well, the permutations of the vertices are all the possible, we could say, displacements, high symmetries that we can achieve in this fashion. So now let's actually go and find all such isometries. So let's start with rotations. Let's consider all rotations that we can get, and also let's keep in mind that, of course, the total number of isometries will be at most 6. So let's start by rotations. So the first rotation that we can consider is the identity rotation, which is a 0 degree rotations that will basically leave the triangle unchanged. So this will be this rotation here. So this will be the first one. Then the second one, we can consider a 120 degrees rotation. This time let's consider it counterclockwise. I'll write it in this shorthand notation like this. And let's think about what it does to our triangle. So if we apply it to our triangle, then the vertices will swap in this way. So B will go in place of C, and then C will go in place of A, and A will go in place of B. And the third rotation which we can think of is a 240 degrees counterclockwise rotation. And let's call it rho. And if we apply rho to this triangle, what we get is, well, B goes in place of C, and then goes in place of A, so we get that B is here, then C goes here, and A goes here. So this is the resulting triangle. But notice that this is nothing but applying R twice to this triangle here. In fact, if we apply R to this triangle here, so R of C, A, B, what we get is A, B, C, which is precisely this triangle here. So we can call a rho, we can call it R squared. So I'll just substitute here. So, and now consider R cubed. So what about R cubed? Well, R cubed is nothing but, let's try to apply it, is basically R applied to this triangle here. But what is it? It's just the starting triangle, meaning this means that R cubed is the identity. So we will later introduce in the course the notion of order of an object. So keep this in mind maybe for later. For now we won't discuss it. And we will I'll just say that it's pretty intuitive to understand what it means. Well, then rotations have order 3, meaning that the power of 3 of such rotations yields back the origin. So far we have 3 elements, 3 rotations in particular. We have E, that is the identity, R, and R squared. We now want to find, we wish to find other elements, but we have to keep in mind, of course, that there are at most 6. So once we hit 6, we know that we have all the elements. So let's now consider reflections. So reflections. Well, actually, let's write it in purple. Okay, it's better like this. So now we have a triangle here. So we will later generalize this discussion to like whether the natural number that indicates the number of vertices is odd or even, and but in this case n, which is 3, is clearly odd. So what we have is that this is our triangle. We will have that the axis around which we can perform a reflection and that pass through the point that we keep fixed will pass through the vertex and the middle point of the opposite edge, like this. So we have 3 such axes. So now all we have to check is that these reflections are not equal to one of these rotations here that we obtained before, and they're not equal between each other, of course. I mean, we could actually deduce immediately that these reflections are not the same as rotations, because the rotation we obtained before, basically, for example, R squared or R didn't fix any point. In this case, we're always fixing one point. And And so this is for r and r squared. And for the identity rotation E, notice that we are fixing all the points, but here we're only fixing one. So we're sure now that they won't be rotations. We now have to check if they are different between each other. So let's see. And we also want to see the result action on the triangle. So let's label these rotations as S1, S2, and S3. So let's start by S1, and let's call, actually let's label the vertices, like the line that passed through the vertices that we're fixing. So let's consider this reflection here. So where we're reflecting about this axis here, we'll notice that this will just be BAC, this triangle here. What about SA? SA will be the reflection around this axis. So, and what will it be? Well, it will be ABC, like this. And then SB will be ABC, okay. Around this axis, the result is CAB. Notice that all these triangles are different. So we have that the total number of isometries is well, the identity rotation r squared, and then SA, SB, SC. But notice the cardinality of this set is 6, and the number of elements that we expected to be in this set should have been at most 6. So we conclude that we have all the 6 isometries of the triangle, or the equilateral triangle. So now we will pick a notational convention, and we also give a definition. So, okay, and that is the dihedral group of order 6. So we call the dihedral group of order 6 that we sometimes denote D3 or D6. It really depends on, well, the conventions adopted by a particular textbook or course or whatever. We will stick with this convention here, but sometimes we could switch convention. I'll just say when we do. It's the following, as I said, is the following number of rotations and reflections, and of course that's order 6. And what we're left, and of course geometrically, as we explained before, it is the group of symmetries of an equilateral triangle. And so this is the dihedral group of order 6. So now, of course, in our definition, we call this the dihedral group of order 6, but we have yet to prove that this is a group. So let's actually go and prove it. So we state fact. So we'll say D3 under composition, that we can denote with this circle here, of these well, symmetries is a group. So let's prove it. So for the first property, which is associativity, we will skip it because, well, since we're considering the compositions of these symmetries to be just compositions of functions that act on this regular polygon, associativity is a property of function composition in itself, and so we already have this verified. So now let's look for an identity element. And actually, a good way to spot an identity element, as we did with the previous examples in the previous video, we could actually draw a Cayley table for this group. However, or for this actually algebraic structure, we will now prove that it's a group. But we can see that, as we also mentioned before, and we will now motivate the definition that we gave of this rotation, the identity element will just be the identity rotation E. Well, why is that? Let's try to think about it, because whatever transformation we apply to the triangle, which can be R squared, S, SA, SB, SC, or whatever, since E will keep the vertices completely unchanged, or whatever triangle, whatever, say, reordering of vertices of the triangle we had possessed. So we will have that the result will just be the triangle inside. So, and it doesn't matter if we apply it inside or outside, or for example, if we have RE of the triangle before, then will just be R times, well, E this triangle, which is just the triangle itself, and thus this is equal to R times the triangle. But if we apply now E to R times the triangle, this is again just R times the triangle, because after we will have permuted these vertices with the rotation R, with the 120 degrees counterclockwise rotation, then the identity rotation will basically preserve the permutation of vertices that we obtained with R. So this is some, which we could say, quick reasoning for why E is the identity. For some more in-depth reasoning, let's now build actually a Cayley table for this algebraic structure. So we have E, then we have R squared, then SA, SB, and SC. Then we have here E, R squared, SA, SB, SC. So let's now build the rows and columns. I'll do it pretty quickly now. So let's start by the first row, so E. Well, E times C is E, and for the reasoning we showed before, E times R is R. E times R squared, well, it's just basically, R, and E times R squared, well, imagine applying again the identity rotation to rotation counterclockwise by 240 degrees. It will just keep the changed vertices in place, so it will just be R squared, and for the same reasoning, E times SA is SA, SB, and SC. Now let's go to the second row. Well, R times E is just R. R times R is R squared, and R times R squared is just E. Remember, for the, we said above that it's basically 360 degree rotation, which is just the identity rotation. So now let's consider the more interesting, we could say, computations, which is R times SA. So the reflection around the vertex A. So okay, like this. So we have our triangle here, and this is our vertex A. So like this. So we first reflect around this line, and then we apply a 120 degree counterclockwise rotation. So let's see what we get. This will be A, this will be so like this. The vertices will be changed in this way. But now you should recognize something. Go back to the starting triangle, and you can notice that this is just the reflection around C. So this is just SC. Like this, so they changed. So now let's do the same for SB. So let's go to the starting triangle, A, B, C. Let's reflect around B. Well, this will be like this. And then let's see that if we rotate 120 degrees counterclockwise, what we will get is the following. So triangle, but again, this should remind you of something. This is just SA, because we just, as you can see, switched. We just reflected around this axis here. And again, by the same reasoning, we can find R times SC. SC is this, and then if we rotate 120 degrees counterclockwise, we get B here, A here, and C here, and this is just SB. So now let's move to the third row. And again, R squared times E is R squared times R is the identity, and R squared times R squared is R. Now for R squared times SA, let's go back to our triangle, ABC. Let's reflect around A. And now let's see that if we rotate 240 degrees counterclockwise, C will go here, A will go here, and B will go here. But notice something. This is just SB. Now, let's go back to our starting triangle, and let's reflect around this time around SB. So we get A here and C here, and if we rotate 240 degrees counterclockwise, we get B here, we get A here and C here. But again, this is just as C, and if we reflect around C and rotate 240 degrees counterclockwise, we just get as A. You can quickly see it, why. And this is for the third row. For the fourth row, the identity times SA is just SA. Now SA times R, let's see what it is. So imagine we reflect the triangle that was rotated 120 degrees counterclockwise. So the following triangle basically, B, C and A, like this. So we'll now reflect around the vertex A, which will just be C and A, B. But notice that this is nothing but SB. So this is SB. Now let's multiply SA with the triangle rotated 240 degrees counterclockwise. So this will just be A, B, C, like this. And now reflecting around A, which is actually B in this case, we will get B, C, A. But notice that this is just SC, so this is the result of this multiplication, SC. So now let's consider SA squared, and SA squared is the equilateral triangle ABC. Let's think about it. We basically reflect around A twice. So first switch B and C, and then we switch back. So we get again C and B. So we get again B and C. So this will just be the identity rotation. So this is the identity, and this is in general valid for all these reflections. So for example, SB times SB is the identity, SC times SC is the identity. So this C here is not clearly visible. And also, let's fill also these other two boxes, which are pretty immediate. Now, I will fill the last two boxes of this table, which is SA times SB and SA times SC, and then I'll let you fill the rest of the boxes as an exercise. So let's see SA times SB of A, B, C. Okay, so this will be SA of, well, B, and then AC here. And the result of this is now CBA, like this. But notice that this is just R times ABC, the triangle, because this triangle rotated 120 degrees counterclockwise. So this is R, and let's see SA times SC. So it's of the same triangle as before. It will be SA of C and BA switched. So reflected, and the result of this reflection will be, well, B, and then here A, and here C. So in this case, notice that starting from the initial triangle ABC, we got a 240 degrees counterclockwise rotation. So because see here B is switched in place of A, which is exactly if we rotate it 240 degrees, then C in place of B and A in place of C. So this will just be R squared. Okay, so here it is. And from this table we can now deduce that this set here under composition is actually a group. So why is that? Let's see. So first of all, we notice that each row, well, we said already that the identity is E, so it's okay, and it's associative. And now let's look at the inverses. So we notice first of all that every row has a column such that the resulting row-column intersection is the identity. So each element has an inverse. Let's explicitly state what that is. So for E, its inverse is E. For r, its inverse is r squared. For r squared, its inverse is r. For SA, its inverse is itself. For SB, its inverse is itself. And for SC, its inverse is itself. So we have that D3 is a group, yes. So we have proven the statement that we claimed above. So now for some other considerations that we can make, let's notice that we can actually build all the elements of this group out of only 3 rotations and 1 reflection. And the reflection we can pick is really arbitrary, but let's pick the one around C. So this one SC, and let's call it just S. So let's see that for the consideration we made above, SA will be nothing but r squared times S, and SB will be r times S, as you can see here. So we have that our group D3 is comprised of E, R squared, R, S, R squared, S, and S. And so this is our dihedral group of order 6, so the symmetries of an equilateral triangle. So now we can move on to the 4, but actually I'll leave it as an exercise to check that, so actually to explain why there are only 8 symmetries of the square. So in other words, the size, so the order of D4 is 8. And furthermore, build a Cayley table for it. So this will be a short exercise to do. And now we will actually directly move to a general n-gon. So we want to prove in general, so the goal now is to prove that for an n-gon, the order of the nth dihedral group is 2n. And we want to generalize many facts that we observed with the equilateral triangle that you will observe with the square here, with D4. So let's start proving these results, but first we will need some introductory ones. So let's state here a preparatory result, and that is that every point on a regular n-gon is uniquely determined by its distances to adjacent vertices. Of said polygon, of course. So let's actually prove it. So now suppose that we have a point A, B, so 2 vertices that are part of this polygon that we call pi, and let's suppose that they're adjacent. So adjacent, we mean that the line segment AB is an edge of our polygon. So we will have something like this, and then the polygon is continuing. So now what we want to show is that there are no 2 points on the polygon that have the same distance to both A and B. So let's suppose there were maybe two elements, such that so maybe 2 elements that we can call R and S in P, such that the distance of R to A and the distance from R to B, and these couple of distances were the same. So in other words, R and S have the same distance to A and the same distance to B. Let's for now just consider 2 points that have the same distance from A and the same distance from B. So we can imagine like a infinite number of concentric circles around A and B. We have not specified a specific distance, so we can pick an arbitrary one. So let's pick a circle of radius, we could say r, around A. Another one of another radius r2 maybe around B. And we look at their intersection. So we can call these points P and Q. So we notice that the radiuses of the circles that we draw are arbitrary. And what we have is that P and Q have actually the same distance to A and the same distance to B. So because dQA is equal to dPA, that is R1, and dQB is equal to dPB, which is R2, as like this. So in particular, we know that if we call this a circumference CB and this circumference CA, then their intersection is at most comprised of two elements. So we have that the two elements of this intersection are precisely in this case, if we suppose that there are two elements, they are R and S. So we can say that CA intersection CB is precisely R and S. But from the picture we made here, and from properties of circumferences and intersections of circumference, we see that the points which have the same distance, so this couple of points which have the same distance to this pair of edges, of actually vertex of the adjacent vertices, lie on opposite sides of the edge formed by these two vertices. So what does it mean? It means that only one of these two belongs actually to pi, because, well, of course we know that it is not possible in a regular n-gon to have like two points that belong to it on opposite sides of an edge. So this concludes the proof for this fact, and now we're ready to prove this general result that holds for dihedral groups of general order, and that is that the order of the nth dihedral group is 2n, meaning that we can now call, this will justify us calling from now on the group of symmetries of a regular n-gon simply the dihedral group of order 2n. So let's prove it. So we'll proceed with this proof into basically we'll proceed with this proof in the following way. We will first prove that the size, so the order of the n, is less than or equal to 2n, utilizing this result that we proved earlier, this proprietary result, and then we will prove that dn is greater than or equal to 2n by finding an adequate number of isometries, of symmetries. And once we will have done that, we will have proved that the order is precisely 2n. So let's start by proving that the order is less than or equal to 2n. So how can we do this? Let's visualize our n-gon like this. So we have a vertex here B, a vertex here A, a vertex here P, a vertex here Q maybe, and then so on. Now let rho be an element of the n, so a symmetry of this regular n-gon. Now we know that we required, before when you define what we wanted our dihedral group to be, that this symmetry must move the shape back in place. We made the example of having like this n-gon on a table and lifting it up, moving it and putting back on the table and having it to fit maybe a hole carved in it, so that, you know, like this maybe, to give an intuitive explanation of the dihedral group. And of course, in order for it to fit back in that hole carved in the table, we would require that adjacency is preserved. So we will have that if B and A in this case are adjacent in this n-gon, then we would want rho B and rho A to be adjacent again, where we denote here by rho B and rho A we could say the image of these vertices under this symmetry. So now, by the previous fact, we know that for each vertex of the n-gon, each vertex of the n-gon is uniquely determined by its distance from two adjacent vertices. So we will have that, imagine that P here or Q here are two vertices of the original n-gon. If we take their image under this symmetry, then they will be uniquely determined by the distance to two adjacent vertices, for example, row B and row A, meaning that this holds for row P, row Q, and for any other, for any vertex different from B and A. So we have that all vertices of the, we could say, image of the n-gon on the row are determined by row B and row A. So by the position of a couple of vertices. So the position actually of the image of a couple of vertices, of adjacent vertices. So now, if we have an n-gon, we have n vertices, meaning that we have n possibilities for row A, for example, say. Now, for the second one, we now have two possibilities, because in a regular n-gon, we only have for each vertex, we could say A, we can have a adjacent vertex here or an adjacent vertex here. So there are two possibilities for the second one, meaning that the total possibilities for the rearrangement under a symmetry will be at most possibilities for rearrangement under row, which is an isometry, will be at most qn. And this is the conclusion for the first part of the proof. Now let's prove that the order of d to the n, dn is greater than or equal to 2n. So now, in order to prove this, we wish to find at least 2n elements that are at least 2n elements of dn, meaning at least 2n symmetries. So we start by rotations. Now, for rotations, we notice that if we have an n-gon, as we showed before, rotations are given by, we can have actually n distinct rotations. And what are these? So n distinct rotations. And these are the identity rotations, meaning 0 degrees, and then r squared, ... up to r to the n minus 1. And what is r? By defining r, we will define all the other rotations. R is a rotation by 2 pi over n radians. So where n is, of course, the number of vertices of our n-gon. And so what will r squared be? R squared will be 4 pi over n, and so on and so forth, up until r to the n minus 1 will be a rotation by 2 to the n minus 1 pi over n. And each one of these is different. So we found n rotations. Let's now search for reflections. So reflections. So for reflections, we will have to think a little bit more, but the reasoning will still be quite simple. So before, if you remember, we mentioned that for our triangle, and this is actually also true, for example, for the pentagon, the lines with respect to which we basically performed our reflections passed through the vertex around which we would reflect all the other ones, and the midline here, the drawing is not it's not really precise, so you can see it well, but this triangle you can see it a little bit better, and the midpoint of the opposite edge. Now let's consider a regular n-gon with a even end, for example this square here. So if we take our a vertex, for example, we see that to perform reflections on this square, we'll have that the line with respect to which we will perform reflection will pass through pairs of opposite edges, or alternatively connecting the midpoints of opposite edges. So this also is a line with respect to which we can perform a reflection, and this also is one. So this reasoning actually holds for general n. So let's express it here more concisely. So we'll have that for odd n, so for numbers of vertices of our n-gon, we will have a reflection connecting each vertex with the midpoint of the opposite edge, and this is in total n reflections, and reflections which are all different. Why are they all different? Because each one of these reflections fixes a different point, in particular the point that we stated here, so this vertex here. Now let's see and actually this proves this statement for odd n. So this is actually, we already proved this for odd n. Let's now prove it for even n. We will have, so think about it. How many lines are there that will connect opposite vertices? So two opposite vertices, there will be on an n-gon, there will be n over 2 such lines. So we will have n over 2 distinct reflections that will connect opposite vertices. And it's not over, because we will have n over 2 distinct reflections that will connect midpoints of opposite edges. And now, by noticing that with this reasoning we have obtained that the n will have n rotations, and in the case for odd n we will have n reflections, for even n we will have n over 2 plus n over 2 reflections. That means that in both cases you have n reflections. This yields a total of 2n symmetries, and this actually proves our result. So we have that, in this case, this actually proves that the n is greater than or equal to 2n. But before we prove that the n is less than or equal to 2n, this implies, so all the stuff that we talked about in this last lines here, implies that the order of 2n is precisely, of dn is precisely 2n. And this concludes the proof of the theorem. So now what remains to be proven is that the dn under composition is actually a group. So we will have to explicitly find an inverse for each element and explicitly find an identity. So before we do that, actually let's state the following fact, which is a direct generalization of what we observed with the equilateral triangle, and that is that the n reflections of dn are s, r times s, r squared times s, up until r to the n to the minus 1 times s, where s is really where s is just a reflection across a line through any vertex, so an arbitrary reflection. So let's prove it. So first of all, we want to prove that all these objects are distinct, but these are actually all different because we're applying these rotations, which are e, r squared, up until r to the n minus 1, to a regular n-gon that has been reflected through an axis. So this will yield all different rearrangements of the vertices of the n-gon. So this is okay. So now what is remaining to show is that all these n symmetries must actually not be rotations, so they must be reflections necessarily. So let's see why that is the case. Because so suppose m and l are natural numbers, and let's suppose that r to the m times s is one of these elements of this group of symmetries. Well then, if we were to suppose that this was actually a rotation, say r to the l, then what we could say is that, well, from this fact here, which is above, from these considerations about rotations that we made above, we already know that the inverse of r to the m counterclockwise 2 times m times pi over n radians rotation is just basically, it's just 2 pi minus that. So, which is 2n minus m pi over n. So we know that there is an inverse. We can denote it also as just r to the minus m. So by multiplying both sides of this by the inverse of r to the m, r to the minus m, we'll get that s is equal to r to the l minus m. But this will imply that s was a rotation, but s in fact it is not a rotation, it is a reflection. So this is a contradiction with what we know about the dihedral, the elements of the n, and so we must deduce that all of these are distinct reflections. So these symmetries are actually n symmetries, from which we conclude that these are actually the expressions for all the n reflections of d to the n. So now we conclude everything with a proof that dn is a group. So dn under composition is a group. So now let's prove it. So for associativity, as we said before, it is verified by the fact that we're considering these actions on these n-gons as just functions, and it is satisfied by composition as function is associative. Now, the identity element is the identity 0 degrees rotation E, and the inverse, well, the inverse for each element, we said already, we already found an explicit form for the inverse of each rotation, meaning that if we want to write it a little bit more, we could say in a little bit more extended way, we'll have that the inverse for E is E, the inverse for R is R. Well, if n is the order of the group, then r to the n to the minus 1, then the inverse of r squared is r to the n minus 2, and so on. And the inverse of r to the n minus 1 is r. And for symmetries, on the other hand, for the same considerations that we made with the equilateral triangle, we see that if we reflect all vertices with respect to an axis like that 2 times, we will get this, the n-gon that we reflected back. So we know that for each reflection, s squared will be the identity, meaning that again, using the notation that we talked about before, but we have not yet introduced formally, that all rotations have, actually all reflections in dn have order 2. So this is another fact that follows from this consideration. So, and well, we have found an inverse for each element. We have an identity, and this is associative. So we have that dn is a finite group of order 2n. However, notice that this group is not commutative. Why? Well, a good argument for it would just be to look at the Cayley table for d3, which is of course a particular example of dn, but it already proves that dn in general is not commutative. So if you take, for example, r times sa, notice that r times sa is sc. But now take sa times r, and sa times r is rb, is sb. See here. And these two are not the same. So of course the dn is in general not a commutative, not an abelian group. So with this we have proven what we wanted to show. So the n is a group. And we will now conclude this video with just some basic facts, last facts about the dihedral group. So the first of these last facts that we will prove is the sometimes known as the commutation relation for between rotations and reflections, and that is the following. We will have that s times r times s to the minus 1 is equal to r to the minus 1, and the proof of this fact is pretty immediate. It follows from the fact that, well, from this fact right here, we know that r times s is a reflection. But from these considerations here, so since we know that every reflection is order 2, then we know that r times s, so r times s is a reflection, so r times s squared is the identity. In other words, r times s times r times s is equal to the identity. And now you can immediately see that just by manipulating a little bit the expression, in particular by multiplying both sides by r to the minus 1 on the left, so r to the minus 1, rs times rs is equal to r to the minus 1, but this is but the left hand side then just becomes s times r times s is equal to r to the minus 1. But since s is a reflection and has order 2, meaning that s squared is equal to e, then we have that s will be equal to s to the minus 1, so it's its own inverse, of course. And from this it follows that from this it follows that s times r times s to the minus 1 is equal to r to the minus 1. This is our commutation relation that we wanted to show. So with this said, I think we have covered enough for an introduction to dihedral groups, for a beginning of an abstract algebra video series. And in the next video, which will be the fourth video, we will cover actually some more examples of groups, such as, for example, the integers modulo n under addition, or u to the n, we will see what that is, under multiplication mod n, and the general linear group, the special linear group, as well as other, and also some applications of symmetries, of symmetry groups to sciences. So with this said, I will conclude this video.